Okay, so in this video, I'm going to do the last non-homogeneous second-order differential equation with a Heaviside Step input before moving on to the very exciting area of convolution. And number one, what it is, and number two, why is it so relevant to Laplace, and why is it so useful for inverse Laplace transforms that are very difficult to solve. So let's have a look at this one. And with this input, we've got an input that has been turned on and been turned off after the space of a second. So, for instance, in real life, you might have a voltage that, or a DC source that's been turned on for a very short period of time, and we want to know what the response in the circuit's going to look like. So let's have a look. Another example might be infusion of a drug into the body between a certain time frame, and you want to see how the response of the vascular system is going to respond, for instance, which might behave in some kind of second-order differential motion. I don't know, because I'm not a biomedical engineer. So let's have a look. We've got f double prime t plus f prime t plus f of t equals g of t. We're not told what g of t is, but we're given this kind of mapping over here, and we're told that this is what g of t is. So let's first of all describe g of t. So we can say that g of t equals, well, the function is 1. It's going to turn on t equals 1, so let's do that. So that's just going to be u t minus 1, which is effectively going to be this, and it's going to be 1 forever and ever and ever. And we need to subtract from that the one function that turns on at 2, minus ut minus 2. Because what that's doing is that it's saying, we'll take this function over here, which is like over here, and then over here goes on forever, and we're going to take the function, if I just draw it above, we're going to take the function, whoops, I'll draw it below, of ut minus 2, which will kind of go all the way to here, and then turn on. And if this is 2, and this is 1, then if we subtract from this one, we're just going to be left with that little thing kind of in the middle over here, which is what we have over here. So that's how we can see that the function g of t is ut minus 1 minus ut minus 2. So we can now, let's just rewrite this. Let's let f of t equal x, and we can rewrite what we have. So we can say x double dot, so that's just the second derivative of the function f of t, plus x dot plus x equals u t minus 1 minus u t minus 2. Okay, and then we can write down the Laplace transforms that we know. So the Laplace transform of x is x bar, and that's just going to be f of s. Then we can say that the Laplace transform of the first derivative of the function is going to be sx bar minus x naught. Then we can say that the Laplace transform of the second derivative of the function is going to be s squared x bar minus sx naught minus x1. And I'm just going to write the next one. Not that we'll need it, but it's good for practice. I can say that the third derivative is going to be s cubed x bar minus s squared x naught minus sx1 minus x2. And then we can say that the Laplace transform of u of t equals 1 on s. We can say that the Laplace transform of ut minus c is going to be e to the minus cs on s. And we can say that the Laplace transform of ut minus c, f of t minus c, equals e to the minus cs dot f of s, providing that the forward transform of f of t yields f of s. So now I'm going to take the Laplace transform of the left-hand side, and then I'm going to take the Laplace transform of the right-hand side. Exploiting the principle of linearity, we can say that the Laplace transform of a sum of components is identical to the Laplace transform of each individual component summed together. So I'm going to go straight into that, and I'm going to take the Laplace transform of all the individual components and add them together. So I can say s squared x bar minus sx naught minus x1 plus the Laplace transform of x dot, which is going to be sx bar minus x naught, plus the Laplace transform of x, which is just going to be x bar, equals the Laplace transform of ut minus 1, which is going to be e to the minus 1s on s, minus the Laplace transform of ut minus 2, that's just ut minus c, e to the minus cs on s, so that's just going to be e to the minus 2s on s. Yeah. Now we know that the initial conditions are such that the first derivative, when t equals 0, is 0, as is the function. So we can say that x0 and x1 are going to be 0. So we can rewrite this. And we can say that s squared x bar minus 0 plus s x bar minus 0 plus x bar equals e to the minus s minus e to the 2s. 1 minute, have I done something wrong here? Yeah, it's not e to the minus 2s, isn't it? That was naughty. Yeah, it's going to be e to the minus 2s on s. So it's going to be e to the minus 2s on s, all on s. So now what we can do is find an expression for x bar, and then take the inverse transform of x bar, then the inverse transform of what x bar equals, and then that should give us x, i.e. f of t. This is always the general approach when solving differential equations using Laplacian methods. So we can say that x bar, s squared, plus s plus 1, equals e to the minus s minus e to the minus 2s on s. And therefore we can say that x bar equals e to the minus s minus e to the minus 2s on s times s squared plus s plus 1. Now, s squared plus s plus 1 is a non-reducible quadratic factor. So we need to think about how we're going to find the partial fractions of that. So the first thing that we can do is just take e to the minus s minus e to the minus 2s out of the equation. There's an expression. I'm not really taking it out of the equation. Taking it out of this part of the equation. 1 on s times s squared plus s plus 1. Okay, so what to do from here? So we can find the partial fraction of this by saying the following. Okay, so now we have x bar in terms of its partial fractions, as a being 1, b being minus 1, and c being minus 1 as well. So the question is, how do we simplify this even more? So when we have a non-reducible quadratic factor, we need to find a way of separating the variables to a point where we would be able to recognize a transform, an inverse transform. And that's quite difficult over here. So what we can do is complete the square by doing s squared plus s plus 1/4 minus 1/4 plus 1. So we can say that that's going to go to s plus a half squared plus 3/4. Or we can say s plus a half squared plus 3√3 on 2 squared. It's exactly the same thing. Square root of 3, root 3 is 3, square root of 2 is 4. And the reason why I did that was because I want to try and get this into a form that I can recognize. And I know that a lot of the trig identities for Laplace forward and reverse transforms are going to be in s squared plus a squared. So that's always a good idea to get into that form. Now we can rewrite this as x bar equals e to the minus s minus e to the minus 2s, 1 on s minus s plus 1, all on s plus a half squared plus root 3 on 2 squared. Now we're moving in the kind of direction where we can see we're going to have something like a on a squared plus s squared, or something like that. So let's carry on. And let's expand everything that we have over here. So we can say that x bar equals e to the minus s minus e to the minus 2s on s minus s plus 1 e to the minus s minus e to the minus 2s all on s plus a half squared plus root 3 on 2 squared. Yeah, so we've just expanded that. Now let's carry on with the expansion. So we can say that x bar equals e to the minus s on s minus e to the minus 2s on s minus, this is where we need to be very careful, s e to the minus s minus e to the minus 2s plus e to the minus s minus s e to the minus 2s, all on s plus a half squared plus root 3 on 2 squared. So we can now see that we have here 1, 2, 3, 4 terms on s plus a half squared plus root 3 on 2 squared. So hopefully we can start to recognize that this is going to be a sum of 4 individual Laplacian components here. So and we can exploit the principle of linearity and deal with them separately. So let's go ahead and do that. So we can now say that x bar equals e to the minus s on s minus e to the minus 2s on s minus s e to the minus s on s plus a half squared plus root 3 on 2 squared plus e to the minus 2s on s plus a half squared plus root 3 on 2 squared minus e to the minus s on s plus a half squared plus root 3 on 2 squared plus s e to the minus 2s on s plus a half squared plus root 3 on 2 squared. Okay. Right. So now we can start to see a little bit about what's happening here. So we've got, just to write the transforms down so that we have them. We've got the Laplace transform of u of t equals 1 on s. We know that the Laplace transform of ut minus c is going to be e to the minus cs on s. We know that the Laplace transform of ut minus c, f of t minus c, equals e to the minus cs f of s for the Laplace transform of f of t equals f of s. So now that we have the transforms just written down, we should be able to start to solve this now. So let's look at the first term. So we can say that x equals, so e to the minus s on s, so that should register as u t minus c. So that's going to be u t minus 1 minus u t minus 2. Now for this term over here, s e to the minus s on s plus half squared plus root 3 on 2 squared, we can see we've got an e to the minus s, e to the minus cs dot f of s. Can you see that here? E to the minus 1s. So we know that it's going to be, so the inverse transform of e to the minus cs f of s is going to be the inverse transform of the Laplace transform, which cancels the Laplace operation. So that's just going to be ut minus c f of t minus c. So we just need to figure out what f of t is, if f of s is the product of e to the minus 1s, which is s on s plus a half root 3 on 2. So if we just write that down, just for clarification, we can say that c, in that case, is going to be 1, and f of s is going to be s on s plus a half squared plus root 3 on 2 squared. So that's going to produce f of t of, we can see it's going to be an s on s squared plus a squared, so it's going to be something that looks like cosine. Cosine a is going to be root 3 on 2, root 3 on 2 t. But remember that we have a shift going on here. Yeah. So do you remember we said in the first shift theorem that the Laplace transform of e to the minus at f of t equals f of s plus a, providing that the Laplace transform of f of t is f of s. So if we can say now that f of s plus a, whenever there's an s, we do an s plus a, we notice that we run into a problem here. And the problem is that there's not an s plus a on the numerator, only here in the denominator, and that's a big problem. So what we really need to do is add in a plus half over here, like that. And then the complication is that we need to take away a half. So this is actually getting quite a difficult question now, because what we need to do is go from here. Okay, so what I'm going to do, I'm going to isolate this guy over here. I'm going to bring him down. And I'm going to say e to the minus s dot s on s plus a half squared plus root 3 on 2 squared. And we need to get that into a form that we like, that we're happy with. It's got to be an s plus a half. So I'm just going to stick in a plus a half over here, just like that. And then we need to take away a half. S plus a half squared plus root 3 on 2 squared, like that. So now we've just converted it into something that we can hopefully find an inverse Laplace transform of. And remember, this here, that what we've said over here, is exactly the same as what's enclosed in these red brackets over here. So if we were to take the inverse transform of this thing, that would produce, oh boy. So over here, we've got something normal? Yeah, we've got an s on s squared plus a squared, so we've got a cosine of root 3 on 2t, but we've got a shift going on of plus a half. And remember that we said here that from the first shift theorem, that the Laplace transform of e to the minus at f of t is going to be f of s plus a. So wherever we have an s, we add an a, which is a half. So we're going to dot product this with e to the minus 1/2 t. I think that is correct. So that's going to be the inverse Laplace transform of that thing over there. Now we have to consider the inverse Laplace transform of this thing over here, which is going to be minus. Please be a little bit easier. No, you're not going to be easy, are you? So this is going to be a on s squared plus a squared, so we've got a sine going on. We've got a sine root 3 on 2t. And that's going to be dot product with the shift of e to the minus 1/2 t, not e to the minus half t. Wow, this is quite a challenging question. And that's only this little bracket over here. So we can say that, there's a way to make this a little bit simpler. No, not really. This is a difficult question. Or just do Laplace of minus 1. Okay, so that's that bit over there. Now let's do the next bit over here. Well, at least the first bit's easy. Ut minus 1 minus ut minus 1. Oh, and we've got to remember this is minus. This is subtracting that thing. So we've got to bear that in mind. And then we're going to say, can we do e to the minus 2s on this thing over here? Is that going to be a bit more straightforward? It's going to be a on... No, it's not going to be more straightforward. It's going to be just as blinking difficult. So let's write down that one over there. over here. So we've got e to the minus 2s dot 1 on s plus a half squared plus root 3 on 2 squared. So we've got something of the form a on s squared plus a squared, but we need this to be root 3 on 2. So that it produces the sine forward transform. If we multiply that by root 3 on 2, then we need to divide. Then we need to multiply this by 2 on root 3. Oh, it is going to be a bit easier. Yeah. Okay. So the inverse Laplace transform of that great big ugly thing is going to be oh boy. I've just realized that what we've done over here was not including e to the minus s bit. That is going to be f of t. So if that's going to be f of t, then we can say that this whole thing is actually going to be u t minus 1 dot this whole function here, which is going to be cosine root 3 on 2 t minus 1 dot e to the minus 1/2 t minus 1 minus, oh boy, this is hard, sine root 3 on 2 t minus 1 dot e to the minus 1/2 t minus 1. My word, that was quite challenging, that bit. And that's only for the red bracket. We've got to do that 3 more times. But I hope you see where I got that from. So this part over here was just the inverse Laplace transform of that and that. So that gives us f of t. But since it's in the form of e to the minus cs f of s, and f of s is this thing, f of t was this thing. So we know what f of t is in ut minus c, f of t minus c. We know the shift is 1, so then we just incorporate that into ut minus c, which is ut minus 1, and then f of t. And there's always a minus 1 shift wherever there's a t. So let's do this one now, e to the minus 2s, and this thing. So again, we need to multiply that by root 3 on 2 to get it into a sine-friendly function, and then we'd need to multiply by 2 on root 3 to get it back to normal. So we know that if we say this is f of s, and this is e to the minus cs, we know that the t shift is 2. We know that f of t, therefore, must be sine at, sine root 3 on 2 t, yeah? And then there's a shift, dot e to the minus 1/2 t going on as well. So that's f of t. So therefore, the total inverse Laplace operation, e to the minus cs f of s, remember this is f of s. Oh, and remember we have to multiply this by 2 on root 3 as well to get it back to normal, is going to be u t minus 2 dot 2 on root 3 sine root 3 on 2 t minus 2 dot e to the minus 1/2 t minus 2. And that's going to be that one over there. Yep. So we've got this one over here for the first one, and we've got this one here for the second one, which is good. Now let's do the third one. Okay, so that's the third term. So we can say that if this is of the form e to the minus c, oops, sorry, can't see that, we say that's e of the form e to the minus cs dot f of s. And we'll say that the inverse Laplace transform of that is just going to be u t minus c f of t minus c. We can see that this thing over here is f of s. So that implies that f of t, we need to find f of t. Remember, we need to get this into a friendly form. So we can say that we have root 3 on 2 at the top, and then multiply everything by 2 on root 3 to get it back to normal. So we can say that f of t is going to be, this is an a on s squared plus a squared, so that's going to be of the form sine a root 3 on 2t, and there's going to be a shift of a half, and the first shift theorem again was e to the minus at f of t. The Laplace transform of that will just be f of s plus a. So if we have an f of s plus a in the forward direction, which we do, plus a half, we can say that must be in the time domain e to the minus at. So we can say that dot e to the minus 1/2 t. So that's going to be f of t, and we need to multiply that by 2 on root 3. So that gives us f of t, and we know, going back to the second shift theorem, that the c shift is going to be 1. So we can say that's going to be equal to 2t minus 1 dot f of t minus c. Well, f of t is this, so it's just going to be dot 2 on root 3 sine root 3 on 2 t minus 1 dot e to the minus a half t minus 1. Yeah? And that's going to be for the third term of this term. So I'm going to put a little box around that. Third term. And now let's do the fourth term. So it's in the form e to the minus cs dot something else. And the something else is s on s plus a half root 3 on 2 squared, which equals e to the minus 2s dot s on s plus a half squared plus root 3 on 2 squared. And we need to get that really in the form of s plus a half, so I need to subtract a half as well from that. S plus a half squared plus root 3 on 2 squared. Right, okay, so now we have this thing representing f of s. And this thing is e to the minus cs, yeah? So you can see that this is in the form of e to the minus cs f of s. So for f of t, we need to find the inverse Laplace transform of this great big huge ugly thing here. Oh boy. So that's just going to be, remove the shift to begin with. So we've got s on s squared plus a squared. So that's going to be something like cosine root 3 on 2t. And since we have the shift, that's going to be e to the minus half t dot cosine root 3 on 2t. Minus, here we have, oh bloody hell. We don't want that to be a half. We need that to be root 3 on 2, don't we? Fine. So let's change it to root 3 on 2. And we'll cross out the half because we don't like the half. Well, we can't really just do that. We've got to multiply this by something. Times 1 on root 3. And that's obviously going to give us 1 on 2, isn't it? Yeah. So if we, oh boy, so this is f of t minus 1 on root 3 and then this is going to be a on s squared plus a squared, which is going to be sine root 3 on 2t with a shift of e to the minus half t. So f of t. Right, so now we've got f of t. We now need to find, because remember this is f of t. Yeah, we've got e to the minus cs f of s. We've found what f of t is, so therefore we can say from the second shift theorem e to the minus cs f of s be ut minus c f of t minus c. So we can say, therefore, that the entire thing is going to be u t minus 2 dot f of t, which is this thing. So that's going to be e to the minus 1/2 t minus c, c is 2, t minus 2, dot cosine root 3 on 2 t minus 2, minus 1 on root 3 e to the minus 1/2 t minus 2, dot sine root 3 onto t minus 2. And that should be the fourth term. Okay, so now that we have the function x, or really it's f of t, we can change that to f of t, equals all of this thing. We can now start to collect terms and hopefully make things a little bit easier. So we've got ut minus 1 common to this term, this term, this term, and we've got ut minus 2 common to 1, 2, 3 terms as well. So let's collect those terms and see what we end up with. And now we have a final answer for the differential equation with a partial unit step input. So you can see that was quite an involved question, and we can see that the function here turns on at t equals 1, and then we subtract the function that turns on at t equals 2 in order to get the response. So let's plot this on MATLAB and let's see if any of this makes sense. Okay, so for the differential equation that we've just solved, here's a MATLAB plot of the input. So we said that it turns on at t equals 1 and turns off at t equals 2. So we have this very nice Heaviside input, and we want to find the response. So let's go and turn on the response for what we solved, and let's see if it's supportive of any way. So let's turn on the plot and let's run the code, and we can see the response that we have over here. So it looks like underdamped harmonic motion as the signal is turned on, and then as it's turned off. So you can see that it's kind of going up and up and up, and if the signal was turned, the input, was turned on and remained on here, it would probably continue to go up and up and up like that. But since it's turned off, then you get the instability occurring at 2. I'm just guessing, but I think it's a reasonable assumption to make, or at least a reasonable guess. So it's a little bit like someone displacing something that has intrinsic instability. And then as soon as you've removed your finger from the system, now it starts to oscillate quite violently. So let's extend the time up to 10 seconds. We can see it really is it's starting to gain amplitude quite a lot. Now let's see if we can increase the time up to, say, 100 seconds. So let's go back and see what happens if we go to, say, 52 seconds. So that's quite interesting. It doesn't seem to be increasing indefinitely. What seems to be happening is that it gets to a certain point, a certain amplitude, and then it kind of stays there. And that's quite nice. That's quite interesting to see. As we zoom in here. So that is quite nice. So we can see what the response is. What's interesting is that if we were to just plot, say, the function for ut minus 1, and ignore, and we're not going to subtract what happens at t equals 2, we can see what the response would look like then. So you can see what that looks like now. So that's the response for just for ut minus 1. And if we want to have a look at just the function of ut minus 2, we can see that again over here. So we can see that the function only turns on when t equals 2, and then it goes like that. And what we're doing, obviously, is subtracting from function 1, we're subtracting function 2. And then we end up with function 3, which is the subtraction of both of those. So you can see that over here, how that's changing, which is nice. After doing all that maths, it was quite a challenging question, that one.